The first classification model we're going to talk about is the logistic regression. So you might have already heard about it in other courses or in the past, or read about it. This is one of the models very frequently used. So let's take a look at what it is. So remember we were talking about the regression for numeric prediction. So let's say in that case we had experience as our input variable, as a predictor or input variable. We're going to use it to predict salary, okay, which is also, in this case, a continuous variable. But if we would plot our observations, it would look like this. And we were using, in that case, a linear regression. So it was trying to find a linear relationship, basically try to fit a line that would minimize those error terms. And as you can see here, given what we observe, we can do a pretty good job using a linear fit. But what if the outcomes are either zeros or ones? So that would be a case of a binary outcome for classification, right? If we have yes or no, 0 or 1, false or true, anything like this, it's a binary outcome. So it would look something like this. Let's say now we have experience, and based on their experience, they either, so that the action they take on some sort of a decision they have to make is either a yes or a no. So the outcome is either a 0 or a 1. So if you would plot these, it's going to look like this. So these are the experience. Based on experience, you either do a 0 or you do a 1, a no or a yes. So if you would try to fit a line over here, so you see it's not really, it's going to be a pretty bad job. So if you would calculate these, say, error metrics, it's basically not a good idea to try to fit a line for this sort of a situation. So what if we could have instead of a line, we could have a function, a shape that looks like this green line over here. Turns out we do, and it's called a sigmoid function. So the idea of logistic regression is so we use this intermediary function. Instead of predicting y directly from x, we are going to predict this probability. So the probability is over here. So this our x is going to predict. So we have a sigmoid function. This is the function. This is the sigmoid function. So it's going to establish a relationship between the outcome that we're actually interested in and this probability. So what we're going to predict now is so given this input, where is it going to fall on this line? And if it's above, then we specify a threshold. Usually they use 50%. So you say then, okay, if this, so over this, it's going to be the formula over here. So if it predicts the value of p to be anything above, say 0.5, we're going to assign it to 1. Anything below 0.5, we can assign it to 0. And we can, of course, use different thresholds. So let's take a look at how it's going to work. Again, I didn't elaborate on the details. Let me see over here. Okay. But the general idea is we're using this sigmoid function, and we are going to, so we're writing this as a function of these y over here. So p is going to be whatever you have on this green line. And then you can, of course, transform it. It's going to look like this. Some algebra. And now we can replace this y with this function over here. And then if we can do the math, it's going to look like this. We can plugging in an x, it's going to give us this probability. So basically this value on this green line. So let's take a look. So now for the observations we have, it's going to predict this p. The p with the hat is going to be the predicted p. Okay. For this one, let's say it predicts 80%, and I've chosen a threshold of 0.5. So anything above this, I'm going to assign to 1. Below this, I'm going to assign it to 0. This is how it uses this sigmoid function to, instead of trying to fit a linear regression line, it tries to predict. So basically the function looks like this, and you see it makes sense. If I have these points and I'm trying to fit this line over here, I should be able to do a fairly decent job. So that's the idea of logistic regression. So the predictions that it produces for us are basically these predicted probabilities, which we could then either assign to a user. Usually it's a 50% threshold, the 0.5 threshold, but we can use some other threshold and basically assign anything above that threshold to the 1 outcome class, anything below it to the 0 outcome class. So another model, another algorithm is the K nearest neighbor. So the logic of it is actually pretty simple. This is how it works. Given an input, so again, we have, so this is the ones with the yellow and purple colors. So say these are, we have x1 and x2, and the outcome class is either A or B. Okay, so we just plotted these. We've done something like similar to a scatter plot. Anything that's yellow, we already know. So these are the points we know about. And so how does it? Now I have a new input. How is it going to assign it to a class? That's what it does. It chooses K nearest neighbors, and with the K nearest neighbors algorithm, we have to specify the K. So it's gonna find the K nearest neighbors, and how does it do that? It basically calculates the distance, and usually a Euclidean distance is used. So this is the function for the Euclidean distance, in case you don't know about it. So it basically calculates the direct distance of this point to any of these that fall the nearest, basically 3 neighbors. So it starts with here, here, and here. Okay, think of it as in our case, a circle. If it would be 3 dimensions, it would be a sphere. But the logic applies to whatever number of dimensions. So we could easily just have a number of dimensions. And then it counts how many data points belong to each of the outcome classes. So in this case, 2 belong to the B class, 1 to the yellow class, and then it's going to just do a majority vote. It's going to assign this data point to the group with the most neighbors. So in this case, to the purple class. If I would have done 6 nearest neighbors, how would it look like? So it would find the closest 6 neighbors. In this case, it would be a circle. If it was, again, 3 dimensions, it would look at the sphere. And now 2 belong to the purple class, B, 4 to the yellow class. So it's going to assign this point to class A. So all these models, by the way, produce predictions. So for this new point here, for example, it provides this, say this is from our testing data set. It assigns it to a neighbor, to a class, and we can have, for any of the models we're talking about here, we can have a confusion matrix and calculate all those model evaluation metrics. So the next model that we can talk about is Naive-Bayes classifier. So this one relies on the Bayes theorem, and it might look complicated, but it's rather simple, pretty straightforward. So we have the Bayes theorem says the probability of A given B. So say in terms of classification, we can think of it, the probability of belonging to a class given some data about that observations. So belonging to, say, the A class, having some data about that observation, can be rewritten as this. The probability A given B is equal to probability of B given A times probability of A divided by the probability of B. This is called the prior probability, or prior belief. And when the distribution of this data is normal, it becomes a Gaussian or Gaussian Naive-Bayes classifier, and we don't really need to calculate this. And we'll do an example. This becomes more clear what we're talking about. But again, the gist of it is this is the basic idea, the underlying idea of the naive Bayes classifier. So how does it work? Let me go. Okay. So let's say, again, we have two categories, outcome classes, and we have some observations that are just plotted on this graph here. And to make it, give a more concrete example, let's call these, so these are people that walk, these are people that drive to work, and here we have salary and age. It's X1 and X2, salary and age. These walk, these drive. So now how does the naive Bayes classifier work? Let's say I have a new data point. I want to see what I want to classify it. I want to assign it to one of these two classes, right? So what I'm interested in is probability of belonging to the walks class given the information that I have about this point, basically age and salary. And I want to calculate the probability of belonging to the drives class, or probability of driving, given the information I have about this data point. And then once I have these two, whichever probability is higher, I'm going to assign the observations to that outcome class. So now the only question is then, how can I calculate these two values, right? Probability of walking given these observations, probability of driving given those observations. So that takes us to using that naive Bayes theorem. So just in terms of some terminology, let's say I want to calculate probability of walking given some of these observations on X. This is called the posterior probability. The general probability of walking in our data set would be the prior probability. This is called the likelihood, but the probability of observing what we're observing, basically the specific salary and age for those people who walk in our observations so far. And this is called the marginal likelihood. So let's see how we would calculate them for what we have over here. So you're going to do this, and then this is going to be pretty similar, right? Okay. So first, the probability of walking. So here we have 30 data points. 1, 2, you can count them. It's going to be 30. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. I guess I double counted 1. But for walk, it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 out of 30, so these should be 20. I might be off, but this should be 20. So 10 out of 30 walk. So this is the probability of walkers in general in our data set. So we do not account for the new observation here. And what's the probability of X? So this marginal likelihood. So what we're considering here, we had a new observation, right? But which was this point over here. We want to see what's the likelihood of observing such an observation, basically X for what's the likelihood of X for these observations. So we're gonna use a distance, some threshold basically, and consider any observations we have so far that fall within this threshold. So let's say, think of it as a circle around the center. So it turns out we have 4, so we have 4 people out of these 30, or 4 observations out of 30. Let me go back with this marginal likelihood. Okay, so I have 4 out of 30, we calculated that one. And now the Px given that it walks, so the marginal likelihood of the marginal likelihood of observing somebody similar to what to the new observations was 4 out of 30. So now the likelihood of observing such a thing given it's a Walker, it's going to be, so number, I want the number of similar observations, these x's, out of all those walk. So it's going to be 3 out of 10. And remember, and notice this circle we've specified here. This is going to basically be a threshold in that algorithm. And we can tune this. This would be one of the naive Bayes would be an algorithm that has a hyperparameter. So we can decide what the radius is for the similar observation. So we define how close should the x's be in order to be considered similar to the new observation. So now we have all the pieces we needed, right? What I wanted was, So I wanted the probability of being a Walker given the observations I have, the x, the salary, and age. I calculated the likelihood of being of having a similar observation among the Walkers. I calculated the probability of walking, so the prior and that was 10 divided by 30, and I had this marginal likelihood of 4 divided by 30, the previous step, and now I can just calculate the probability of being a Walker given the observations I have about this guy. So we will do a similar thing for the drives class. And so where do we get these numbers? Let's do it again for this one, just manually. So the probability of driving, the posterior probability of driving given these observations. So I want the prior probability of drivers out of these 30. So 20 out of 30 is basically P of driving. So P of driving. Let's go back to the formula we had over here. Okay, so you're gonna have probability of driving, probability of x giving driver, and this marginal likelihood. We're gonna calculate these. Let's go back. Okay, so this is 20 out of 30 is gonna be the prior probability, and now this is gonna be the same. P of x is 4 out of 30. Now about the likelihood, marginal likelihood was 4 out of 30. The likelihood is so within this radius, what's the probability of being a driver? It's going to be 1 out of these 20. So now we have these two values. Whichever is higher, that's the class we're going to assign this observation to. So it's going to be the Walkers. So that was just the overview of the naive Bayes classifier, how it works. So now let's talk about the next one, which is a decision tree classification. So remember we talked about the regression tree or decision tree regression. So decision tree classification, this is how it works. So let's take again, we have observations. You can think of them as salary or age or any other input. We want to, and the coloring you see is basically the two outcome classes. So the decision tree classifier, basically it wants to split the observations so that it ends up with more homogeneous basically outcome groups. So it wants to split this so that everything in the outcomes is homogeneous, is of one type. So, and how it works is it's going to do the splitting based on some metric. The metrics here for classification, so the information gain we talked about earlier, it can be used for this as well. So it's basically going to, it's try to reduce the entropy, basically have information gain, meaning it wants to reduce the randomness, improve certainty in the resulting splits. So let's say the first split, it does this. So compared to the previous one, the homogeneity of right here is pretty heterogeneous. It's a variation of both of them. It does this split. So these two classes have a say better, there's less variation in them. And now it does this. Okay, now we have a clean cut. It's clearly separates these two outcome classes. Now it does another split. It's still not, we haven't reached the threshold. Again, here the tree keeps splitting until it either, so that the threshold is until we can specify how many, what's the minimum number of observations we want to end up with in our leaves. So let's say it's 6. It could be some number. And it keeps splitting, let's say this. Okay, now I have 3 pure homogeneous classes. It keeps going. Okay, split 4. We have basically perfect separation now. And another metric for deciding till when to split could be, again, a threshold for the reduction in entropy or reduction. Another metric is Gini impurity. We kind of talk about this a little bit more when we do the hands-on exercise. So how is the tree going to look like? It's going to look something like this. So the first cut was the split 1. So it's going to be x2. Let's say this is 60 here. Let me add it. So let's say this is over here, 60. And split 1. Yep. Oh, this was, yeah, 60. And the second split is this one. So this, let's say this one over here is 50. This one over here is 70. And this over here is 20. Oops. So how does it work now? If I have a new observations, I observe the x1, I have the x1 and x2 when I assign it to one of the, either the red or the green class. So let's say my new x1 and x2 is 40 and 30. So it's gonna say, is x2 less than 60? Yes, okay, go this way, it's 30. Is x1 less than 70? Yes, okay, then it belongs to the red class. So it would be somewhere here. So 40, we said x1 was 40. Yeah, it's gonna be somewhere here. And let's do another example. Maybe I should do it in, let's say we have 80 and 50. Bad writing. So x1, x2 is 50. Is it less than 60? Yes. Is x1 greater, less than 70? No. Go this way. Is x2 less than 20? No. So it belongs to the green class. So this is how we use the decision tree. That's the tree it comes up with once the decision tree classification algorithm has trained on our training, has learned from our training data. This is what it creates. So this is the intuition for the decision tree classification. The next one is the random forest classification. So similar to random forest regression, we have a random forest classification. Again, it's an ensemble learning method. It uses multiple decision trees to obtain better performance. It works very similar to what we had before. It basically, we specify how many how many trees we want. Basically, we have to specify how many trees we want, the n. And for each tree, it's gonna pick a random k data point or a random subset of our data set, and then it builds a decision tree based on that. It repeats this process for each of the trees. Let's say we have 10, we specify 10 trees, and then now for a new data point, it's gonna feed it to that tree. That decision tree is gonna make a prediction. Each tree is gonna make a prediction. It's gonna go with the majority vote. So for example, let's say in the previous example, if 7 of the trees predicted the input to be green, 3 of them predicted it to be classified as red, the random forest is gonna say this observation belongs to red, the one with 7 votes versus 3. So that was random forest classification. And the last one we're going to talk about, so by the way, these are all classic machine learning classification algorithms that you may hear or encounter in different scenarios they can be used for. And we're going to go over the overview of pros and cons again. So the last one is the support vector machine. So we say we're going to talk about this, and then we're going to refer back to the support vector regression. That one hopefully is going to make more sense then. The last classifier or classification algorithm we're going to talk about are support vector machines. So these can be very powerful, and you will see based on the idea why that is. So let's say we have these observations. Again, we have just made this simple for the explanation, but it can apply to any number of x's here or n-dimensional space. Basically, we have we observe x1 and x2. So say it's salary and age, and we have two different outcome classes. So this is again our training data here. And we want to find a line that allows us to kind of separate these very clearly. So, I could draw all these green lines, right? And so the idea for SVM is support vector machine is it tries to find a line so that a line that has the largest possible margin between these two classes. So this margin here, so it tries to find a line that has the maximum margin between these two classes. And this line here is called basically the hyperplane, the optimal hyperplane. And this is always going to be one dimension less than the space that we're dealing with. So in this case, we have a two-dimensional, we have x1s and x2. So we have a two-dimensional space, line is in 1 dimension. If we were dealing with a three-dimensional space, the hyperplane would be a surface, right? A two-dimensional hyperplane would be a surface, and so on. We can go up. But for visualization, it's easier to just go with the two-dimensional space. In this case, the hyperplane would be one-dimensional. So let's take it to give a better graphic of what's going on. So what it's trying to do is, let's talk a little bit terminology as well. So it tries to find this line that maximizes this margin. So this is the hyperplane. And support vector is what's called support vector is basically this vector that goes from the hyperplane to the basically the observations that lies at the boundary of that class. So in this case, the green class, or in this case, the red class. Maybe one way to think about it would be, let's say if we are, so these are the basically most extreme observations in each class, that are closest to the observations in another class. So maybe one way to think about it would be if you're trying to classify dogs and cats. So this is basically the cat that is most similar to dogs, and this is the dog that's most similar to cats. Maybe that's one way to think about it. And so it tries to find this line, and that maximizes this margin, and that's what the SVM does basically. We're not going to go to details of the algorithm. It's going to fall. It will involve a lot of technical detail that I don't want to get into for this course. But so this is the general intuition for SVMs. But there is another add-on that improves the power of this algorithm. So oftentimes our data is not linearly separable, right? So here we could draw a linear line. It would work pretty well, give us perfect separation. But oftentimes that's not possible. So there's a thing called kernel trick. And what we will be using is going to basically be kernel SVMs. So it's basically SVM with a kernel trick. And what the kernel trick does is it transforms data into another dimension that allows you to perfectly divide the different classes. So for example, if we had this data set, basically this is the data in our original, the original dimensions. It's a two-dimensional. But if we would take it to 3 dimensions like this, we would be able to perfectly separate these two classes having this two-dimensional hyperplane, right? Another way to look at it is this. So this is a more precise illustration of this. Again, we have two classes. This is in the original space, two-dimensional. The kernel trick is going to transform this. So it's basically going to multiply. Let's think of it. Well, multiply is not a good word to use. Basically, it's going to apply that transformation function. So each observation is going to, that transformation function is going to be applied on each observation, and the result is this basically. So it's transforming these original data into this space, and now it can perfectly separate them with a two-dimensional hyperplane. So this is the intuition of how kernel SVM works. And now the trick is then how to find this. So when we do kernel SVM, there are hyperparameters to tune. So one of them is, and the different names, for example, Gaussian RBF kernel is one of them that we will use. So this is basically just called Gaussian because the type of transformation that's being used is like this. So it's gonna, when it sees something like this, it's gonna transform it using a function to this three-dimensional space. But in this case, we're going from 2D to 3D, but it could be more dimensions, doesn't matter, the concept is the same. But by tuning this parameter here, it's gonna basically change the radius of this circle and allows to perfectly separate the green from the red. That's what it's gonna do by playing around with this hyperparameter. We would find the perfect kernel to then be able to use SVM on it and separate these two classes perfectly. So we're going to see in the hands-on example, we'll play around with this hyperparameter and see how it changes the performance of the SVM classifier. So this was an overview of some classification models. And here, just to sum them up, so we talked about the logistic regression, k-nearest neighbors, SVM and kernel SVM, naive Bayes, decision tree, and random forest classifiers. So here's a list of pros and cons. So logistic regression, again, you remember it was a probabilistic approach. Using that sigmoid function, it would basically come up with, predict the probability of belonging to either class given an input. Then we could use a threshold to explicitly assign it to the class 1 or 0. The cons are there's some assumptions for the logistic regression just we didn't get into. We will come back to it in our hands-on. K-nearest neighbor, as you saw, it's pretty straightforward, simple to understand, and it's also a fast algorithm. But the caveat is you need to choose the number of neighbors, and it's going to change the performance of the algorithm. It could change it. Naive Bayes is efficient, is not biased by outliers. It's going to work on nonlinear problems. It's a kind of probabilistic approach. And it has, though, an assumption. It assumes that the features have the same statistical relevance. So basically that x1 and x2 we're looking at, the salary and age. So if we had, say, 10 predictors, there is an assumption that these features have the same statistical relevance. Decision tree classification, the pro is for sure the interpretability, and we don't need to scale features, and it works on both linear and nonlinear problems. Again, the problem similar to the decision tree regression on small data sets, it's kind of poor for performance, and depending on how we decide to stop the tree, it can overfit easily. Random forest classification, again, is powerful and can be accurate for precision purposes. Interpretability suffers here, similar to what we had in regressions. It's going to be a black boxy model, and overfitting can easily occur and we need to choose a number of trees. And then the SVM is a very well performing classifier. It's, well, once we do the kernel SVM, it's going to be appropriate for nonlinear problems as well. The logic behind it might be a little bit more complex, but it can perform very well, but it can be sensitive to overfitting. And we're going to do an example on some synthetic data and see how that works there. So it was a quick overview on classification. And just a summary of what we talked about in this whole lecture. We talked about supervised learning. We are dealing with labeled data in supervised learning. We are usually splitting our data set, at least into a training and testing set. If the data is large and we have hyperparameter tuning, we could have a validation set as well, which will be used during the training phase, and then eventually we evaluate our models on the testing set. When we have a numeric outcome or continuous outcome, we're talking about numeric prediction. When we have a categorical outcome, we're talking about classification, and time series we didn't get into it. So that was it for that was the last piece of this lecture, and we're gonna do some hands-on activity on numeric prediction as well as on classification.